The Center of Excellence for Global System Science is one of several centers of excellence for computing applications funded by the European Union as part of the European High-Performance Computing Strategy. Coordinated by the University of Potsdam, the consortium includes 2 HPC centers, academic and research institutes, and companies, as well as players that in turn aggregate academia, industry, and public administration. Together, these partners bring together high-performance computing and global systems science. The latter is itself an emerging field that develops evidence and understanding in view of global challenges, such as climate change and green growth, or financial stability, or epidemics. GSS combines stakeholder dialogues with data-driven simulation modeling in order to explore potential future evolutions of the global system underlying a specific challenge and to assess potential consequences of policies, or more generally of alternative decisions. CoeGSS aims to enhance GSS modeling through high-performance computing and high-performance data analytics. Its work is centered around 3 pilot studies. The first one, on health habits, focuses on smoking habits and the tobacco epidemics. The second one, on green growth, looks into a sustainable mobility transition, and the global urbanization pilot analyzes two-way relations between transport infrastructure and real estate pricing in cities. All pilots use synthetic populations and agent-based models. This video briefly shows this approach, taking as an example the green growth pilot. I would like to explain the approach by the Center of Excellence for Global System Science and the tools that it provides for thinking about a sustainable mobility transition. First of all, if we look at mobility today, it's not very sustainable. We have air pollution, traffic jams, more cars on the road every year and bigger cars on the road, leading to congestion. We have accidents and emissions are produced. And there are a few proposed solutions from the technology domain, like electric vehicles, like mobility apps, smart charging, autonomous driving, and more. However, it's not only a technological problem, it has a social dimension as well. It may need new regulations, it may need a reframing of the whole problem, behavioral change, value change of people in order to complete a sustainability transition. And we have to take into account, of course, also the economic dimension of this, including the car industry with its component suppliers, looking at prices, looking at employment in the car industry. So we can really say that mobility is the perfect example of a global system, and global system science and the Center of Excellence for Global System Science looks at precisely these global systems. They are complex and globally connected. They have several dimensions: society, economy, environment, technology, and more. They function on multiple levels, from the city to the region to the nation to the whole globe. And there's a multitude of heterogeneous agents interacting in these systems, and each of these agents then has their own preferences, values, interests, knowledge base. And there is a complex structure of interactions between these agents, complex networks for the interactions between the agents and their environment. So if we want to look at a transition, we are looking for a future that looks fundamentally different from the past. And in order to define that, we need the participation of the agents in the system, of the people in the system, and we need a shared vision and the narratives about how to get from here to this vision. In order to provide some decision support in this problem, global system science uses computer-based modeling based on data and integrates this with stakeholder dialogues in order to co-produce solutions for these problems. So what we use are synthetic populations and agent-based models in order to represent the global system on the computer and run simulations that, as in a virtual laboratory, give the possibility to explore potential future evolutions. This synthetic population is a population of virtual agents that reproduces the statistics of the real population. For example, the age distribution, the income distribution, and further. And these synthetic people are grouped in synthetic households. They have a geographic position, and they may have more features. They are synthetic in two senses. On the one hand, the virtual agent doesn't represent a precise real-world agent, so privacy is maintained because there's a statistical step in between the real population and the synthetic population. And on the other hand, it integrates data from various sources, recording all the data at the agent level, so that data from different fields and of different formats can be integrated. And they allow to model then at the agent level. So one defines the agents with their features, one defines the interaction networks and their interactions in these networks, and then one can observe the system behavior in simulations. So coming to the mobility transition model, which is a model of this kind, produced for the Green Growth Pilot within the Center of Excellence for Global System Science. We use as an example for modeling a country the German population and represent it in terms of persons and households. The persons have features like age, income, gender, and they have a mobility profile which is taken from a mobility survey. And these persons are grouped in households. We have 11 types of households, from one person, young, medium, old, to two persons and more person households. They have a geographic position. And these persons then can choose between 5 mobility options. One is the conventional car, then we have electric vehicles, public transport, car sharing, and not motorized transport, so walking or cycling. And the agents choose between these options based on their preferences, and we divided up these preferences into 4 dimensions. The convenience plays a role, innovation, the costs of this mode of transport, and the regard for the environment. The dynamics in this model are then defined on the agent level. Agents exchange information in a social network at the person level. The household takes the decisions based on the preferences of the agents. And in this picture, we can see that the households are located in a spatial location. The spatial network also has features such as charging infrastructure or population density for each grid cell in a map. And we also have an evolution of some global entities like the market and the evolution of technology. With this whole approach, we can then come back to these discussions or dialogues with stakeholders, for example, to discuss these assumptions and, in case, to refine them, to be able to try out the different consequences of different assumptions in this model. An example could be that we assume for now in the model that the combustion engine cars are more convenient at the moment than electric vehicles because, for example, you have gas stations everywhere, but you might not have charging stations everywhere. And then how these features will develop over the future can be discussed with the experts from the field and the stakeholders interested in these in the results. So as an example, we've looked at 2 different scenarios for the deployment of charging infrastructure for the case of Germany. We have a business as usual scenario which just continues the present trend. And we have a scenario of increased investment in charging infrastructure. And I would now show this show how we can look at a few results from different dimensions and at different levels of aggregation in the outputs of this model. So these are the 2 scenarios that we were just looking at: charging stations, one linear scenario and one increased investment scenario. And for these 2 scenarios, we can now look at different outcomes of the model. For example, the mobility for the country overall. where we see the, for example, the combustion engine decreasing more with the increased investment scenario than in the business as usual scenario, and electric vehicles, which are these green lines here, increasing more in the increased investment scenario. If we want to know something about uncertainty related to all these things, we can look at a different type of view where we get information not only on the average as on this other slide, but also on the uncertainty around these. And we can also look at several runs from the model if we're interested in any of these in particular. We can, in this view, also look at various other outputs in the model. For example, we might look at the mobility dynamics for a region within Germany. This is an example of Berlin, where public transport is rather high and electric vehicles pick up. If we look at a different region, which, just as an example, using North Rhine-Westphalia, the combustion engine cars are at the top of the shares. We can also, because we're using a synthetic population, zoom into different household types. For example, looking at the single-person household with just one young person, then we see these are the people who actually start buying the electric vehicles, while if we take, for example, the household, an older couple, the combustion engine cars make up most of the share. And in order to not only look at these lines, we can also take a spatially explicit view on the results. In this view, we can look at two dimensions in the results at the same time. Here we have the height of the spikes representing the number of charging stations at a certain position within Germany, and the color of these spikes representing the demand for electric vehicles. So we see that in most cases these correspond, so electric vehicles are bought where there are more charging stations, but not in all cases this works. And then this is an indication for going back into this model, understanding better what's happening there, discussing which assumptions are in it, and seeing which assumptions might lead to these patterns. We finally have a map view which plots the results for the different scenarios. Also, we have the linear scenario on the left here and the exponential scenario on the right. And in this map, we can zoom into certain areas. We can look at the map also over time and see that in the exponential scenario, demand for electric vehicles increases much more than in the linear scenario, for example.